Hello and welcome, honor students. Welcome back to chapter 14. I trust that you had a very nice Easter and a little bit of a break, a 4-day break, and got to relax a little bit, clear your mind, and now come back recharged and focused for these last several weeks of school. So we talked about previously in our last couple virtual lessons, we talked about Boyle's law, and we realized Boyle's law is pressure and volume, and we talked about Charles's law in our last virtual lesson, and that was involving volume and temperature, and we learned the relationships to them. Today we're going to talk about Gay-Lussac's law and the key concept: how are the pressure and temperature of a gas related? Now, we looked at and talked about some graphs, and if you talk about a pressure to volume graph, we realize and learn that it is a curved line. If we have pressure and volume, we see a line that comes like that, and that is inversely proportional. That's really important concept there, inversely proportional. So as the volume decreases, the pressure increases, so it's in direct relationship. And we looked at Charles's law, and that was volume to temperature. And we looked at the graph of volume to temperature, and we have volume, temperature, and it's a straight line. We realize the temperature must be in kelvins. It's a straight line because it's a direct relationship. So as the temperature goes up, the volume goes up. That is a direct relationship. And then today, Gay-Lussac's law, and that is pressure to temperature. And once again, it is the Kelvin temperature. So if we look at its graph, we have a pressure, temperature, and it's going to be a straight line. As the temperature goes up, the pressure increases. Think about why. If you are holding the volume constant, you have all these gas particles going faster and striking with more and more energy, that's more pressure on the sides of that container. So therefore, it is a direct relationship and it's a straight line. So we learned that both Charles and Gay-Lussac's is a straight line, whereas Boyle's law is a curved line because it is inversely proportional. Hopefully you jot these down in your notes. This is really important. So I would pause the video, make sure I got these 3 graphs labeled and understand the concept behind them. So as we were talking, Gay-Lussac's law, as the temperature of an enclosed gas increases, the pressure increases. So as the temperature goes up, the pressure is going to go up. So as temperature falls, the pressure is going to fall as well. So here we have this gauge, and we see the temperature here is 300. We double the Kelvin temperature. What happens to the pressure? It doubles as well. So let's get this down in our notes. Here's a definition for you. And each one of these gas laws are a specific definition. So Gay-Lussac's law states that the pressure of a gas is directly proportional to the Kelvin temperature if the volume is constant. And here is our formula. So please make sure you jot that formula down and the definition. If you looked in our Moodle classroom, you will have noticed that I have included a formula sheet, and that formula sheet is very important. So you can print that formula sheet out and you can utilize it through all the worksheets that you will have. And also the test, you'll be able to use that on the test. Now, I will have you add a little bit of information to that formula sheet, but not today. We'll get to that on Friday's virtual lesson. All right, so we have pressure 1, temperature 1 equals pressure 2, temperature 2. So let's think about Gay-Lussac's law. Gay-Lussac's law is applied in the reduced time it takes to cook food if you use a pressure cooker. So in a pressure cooker, food is cooked faster because it's trapping the gas in there. So the temperature is going to rise because now you have increased pressure above the liquid. So now for it to boil, it's going to boil at a much higher temperature than 100 degrees Celsius, which is what water's boiling point is. The pressure rises, which increases the risk of explosion. That's why you have this little valve right here. If you see this little valve right there, that's a safety valve. That way it doesn't get so intense that it actually explodes the lid off. So a pressure cooker has a valve that allows for this vapor to escape so that it does not go above a set pressure. And that's what cooks the food faster, is the fact that the pressure above the liquid is very high, which raises the boiling point, and therefore it cooks at a much faster rate. So using Gay-Lussac's law, here is a example problem, and then we're going to look at several examples, actually 3 of them together. So aerosol cans carry labels, do not incinerate or burn. Notice if you get a can of hairspray or something that is in an aerosol container, it'll also say, do not leave in a hot car. Why? Well, the temperature will increase, which means the pressure is going to increase, which means it could burst the container. So let's look at this problem. This problem will show why it is dangerous to dispose of aerosol cans into a fire. The gas in a used aerosol can is set at a pressure of 103 kilopascals at 25 degrees Celsius. If the can is thrown into a fire, what will the pressure be when the temperature reaches 928 degrees Celsius? So look at the change in temperature. So that's quite an excessive change in temperature there. So the first step is always the same. You write down everything you know. You're going to see as we start combining all these gas laws in the next virtual lesson that it's imperative you write down everything. And once you've written down everything, then you can easily determine what formula you have to use. So we're given our pressure, our temperature 1, our temperature 2, and we're trying to solve for our pressure 2. So you must remember, always just do it first and get it out of the way. Convert to Kelvin. So you write down here, one way I'm going to show you is cross multiply. Set up like that makes it so much easier. T1, P2, P1, T2. And then you can just plug in your information. So what do? They go P2 is equal to P1 times T2 divided by T1, and then they just plug everything in. So look at the pressure now. After they do the calculations, 415 kilopascals. So a tremendous amount of pressure is in that container. So that makes sense. Temperature went up a lot, the pressure went up a lot. So let's look at this problem here. A pressure cooker contains kale and some water that starts at 298 Kelvin and 101 kilopascals. The cooker is heated and the pressure increases to 136 kilopascals. What is the final temperature inside the cooker? So you're in a pressure cooker, which means your volume 1 is going to equal your volume 2. So it's held constant. I'm not going to worry about it. So we have P1 over T1 equals P2 over T2. Quickest and easiest way is split this thing out by cross multiplication, make a line problem out of it. So you have P1 T2 equals P2 T1. How did I do that? I just cross multiplied like that. And that makes it so much simpler to just plug in my information. So now let's write down everything that is given to me here. So I have P1 T1, P2 T2. So my pressure 1 is 101 kilopascals. My temperature is 298 Kelvin. My pressure 2 is 136 kilopascals. And my temperature 2 is blank Kelvin, and that's what I'm going to solve for. So I'm going to just plug this right into this particular problem right here. So I am solving for T2, which I'm going to get rid of P1, cross them off, and now I'm going to plug this all in. So I have P2, which is 136 kilopascals. My T1 is 298 Kelvin. My pressure one is 101 kilopascals. My kilopascals cancel, that leaves me in Kelvin, which is what I'm solving for. So I get my calculator and I go 136 times 298, and I'm going to divide that by 101. So my answer comes out to 401.267, but how many sig figs? I got 3 sig figs. So I'm going to round my answer at 401 Kelvin. So 401 Kelvin is my answer. If I wanted to convert that back to Celsius and find out what that is, that means it went up to from 100, basically it went up from 25 degrees Celsius to 128 degrees Celsius in there. So it was well above the boiling point. So my answer here is in Kelvin, it's 401. All right, so just a couple things before we actually move on to the next one. This is important. Your units of pressure, they do not have to be atmospheres. You're going to see this as we go into the next couple gas laws. It can be kilopascals, it can be atmospheres, it can be torrs, it can be millimeters of mercury. Those are the 4 most common pressure units. The ones when we go into the next section that we're going to be talking and using a lot is atmospheres and kilopascals. And that's the ones we're going to primarily use in that particular section. But you don't always have to convert back and forth to make sure you're in atmospheres. It's not necessary. And let's break it down here. And that's exactly what they've done on this problem. And they got 400 as we did as well. They didn't round it. I rounded mine to 401. All right, now let's look at this particular problem. You might want to pause the video and try it out on your own, and then pick up and see as I break this one down. So pause the video now if you'd like to try this one on your own. All right, so let's take a look at this. The pressure in a sealed, rigid plastic container is 108.0 kilopascals at 41.0 degrees Celsius. What is the pressure when the temperature drops to 22 degrees Celsius? So they're giving me pressure, they're giving me temperature. I don't see anything about volume, but my answer lies right here. A sealed, rigid container. Rigid container doesn't flex, so therefore the volume is constant. So that tells me right away I'm going to be using P1 over T1 equals P2 over T2. So I'm going to write down all of my variables here. So P1, T1, P2, T2. So my pressure one is 108.0, and that's kilopascals. My temperature is 41.0 degrees Celsius plus 273. So I just try to just get that done with. 273 plus 41, so I have 314 Kelvin. All right, what is the pressure? So that's kilopascals, blank kilopascals, and then my temperature dropped down to 22 degrees Celsius plus 273. So that's 295 Kelvin, 295 Kelvin. All right, so now I'm going to cross multiply. So I'm going to go just like that. I'm going to go P1 T2 equals, I'm going to cross multiply again here, P2 T1, just like that. And I'm solving for P2, so I'm going to isolate P2 and go like this, and that cancels off. So now The formula I'm using is P1 times T2 divided by T1, which equals my secondary pressure. So now just plug in my units here. So I have 108.0 kilopascals. My temperature is 314 Kelvin. I'm going to divide that by my temperature 2 is 295. And I'm going to divide that by my temperature 1, and that's what I have on the bottom here, is 314 Kelvin. So please make sure you pay attention to your notations and you follow your formula right. So the T2 goes on the top, which is 295, and T1 goes on the bottom right here, which is 314 Kelvin. Noticing your kelvins cancel off. So now when I plug this in my calculator, 108 times 295 divided by 314. And I have to be at 3 significant figures. So this comes out to 101.5, and then 3 sig figs means 102. So let's make sense of this. The temperature fell from 314 to 295, so therefore the pressure fell from 108 to 104, so it makes sense. Let's look at the next one here. The pressure in a car tire is 198 kilopascals at 27 degrees Celsius. After a long drive, the pressure is measured at 225 kilopascals. What is the new temperature of the air in the tire? So think about what's happening. You're going down the road for a long trip. That means the tire is going round and round and round, and the friction is picking up and causing the air to heat up inside there. So that's why the temperature of the tire is going to have increase, because the pressure increased. So here's a key note: assume the volume is constant. So it's not meaning the tire got bigger. The tire is the same volume. So that means right away Gay-Lussac's law. So I'm dealing with pressure and temperature only. So after I determine that, I can write my formula: P1, T1, P2, T2. So now I'm going to come over here. My pressure 1 is 198 kilopascals. My temperature 1 equals 27 degrees Celsius plus 273 equals 300 Kelvin. Then my pressure 2 equals, it was measured at 225 kilopascals, and it's wanting to know the temperature, secondary temperature in Kelvin. And we can convert that back to Celsius so we have a nice comparison. So first thing I'm going to do again is cross multiply. So I'm going to have right here, I'm going to have P1 T2 equals P2 T1. I'm solving for my secondary temperature, so I'm going to divide both sides by the P1, canceling it off. So I have P2 times T1 divided by P1, and that equals my temperature final. So when I look at my variables I have here, so I'm going to go 225 kilopascals times 300 Kelvin divided by 198 kilopascals. Kilopascals cancel, and that leaves me in my Kelvin temperature. So 225 times 300 divided by 198. So I have to have, and this comes out to, just if I plug in my calculator, it's 340.91. So now I'm going to have to look at my sig figs. So I have 3 sig figs across the board. That means my temperature 2 is going to equal 341 Kelvin. So I can come over here and rewrite that, 341 Kelvin. So if I wanted to know what the Celsius, so I can compare Celsius, so I go 341 minus 273, so it went up to 68 degrees Celsius. So I went from 27 degrees Celsius before the trip and a pressure of 198 kilopascals. After the trip, my temperature went to 68 degrees Celsius and my pressure was 225 kilopascals. So that, ladies and gentlemen, are your three gas laws. We have three gas laws: Boyle's, Charles, and Gay-Lussac's law. And that is example problems. I have worksheets for you. You've already turned in Boyle's. Charles is due today, so please make sure you submit that in your Moodle Dropbox. And Gay-Lussac's will be due tomorrow, Wednesday at 8 p.m., the Gay-Lussac's worksheet. The next virtual lesson I will have is going to be on Wednesday, and it will be the combined gas law. It's exactly what it sounds like. We're going to combine Boyle's, Charles, and Gay-Lussac's into one, and we're going to begin to work with it. And that is, how are the pressure, volume, and temperature, all three of those variables, together related? And we're going to work some example problems, and you'll have a small worksheet for that will be coming out due. So thank you for watching. Go in peace.